Welcome back, everyone. In part 2, we're going to focus on defining the model, defining the loss and optimization functions for the model, training the model, and then evaluating the model. This model, as well as the training of it, is going to look extremely similar, almost an exact copy of what we did earlier. So we'll be copying and pasting a lot of code from the lecture notebook since we've already gone over the code in the previous basic RNN lectures. Let's head over back to the notebook and continue where we left off last time. Okay, here's where we left off last time. Next, we want to define the model, and what I'm going to do, I'm just going to copy and paste this from our lecture notebook, and then basically go over the different things it's doing. And this is essentially the exact same code we've seen before. So I've created an LSTM network class. It's inheriting from rnn.module, just as last time. The input size is 1. However, what we're going to do now is, since this is a more complex data set, I went ahead and expanded our hidden size, those number of neurons inside the LSTM layer, to 100. And then the output size stays the same because we're still just predicting a single point into the future. And then we have our hidden size being assigned with the hidden size that's passed in. We add in that LSTM layer based on the input size and the hidden size. And then we have the fully connected layer. So that's going to be taking that hidden size and reduce it down to the output size, which is just one value because recall, essentially just predicting what's that next value. And then we initialize our hidden state and our cell state. And then for the forward method, what we're doing here is recall that this LSTM reproduces or spits out this tuple, where we're going to assign the first item to LSTM out, and then the second item is that hidden state and cell state, which we are assigned to self.hidden. And then we pass in our sequence, kind of reshaped or reviewed to be in the correct format for LSTM, along with our current hidden state. Then we get the prediction by finally just passing in LSTM out into that final linear layer, make sure it's in the right shape here, and then finally we return pred -1 because we really only care about that last value. So go ahead and run that, and then what we're going to do is instantiate the model and define loss and optimization functions. So we'll say torch.manual seed. I'm going to arbitrarily choose 101, so you make sure all your same randomizations are the same as mine. And then we'll say model is LSTM. We'll go ahead and call the network there. Go to criterion. We'll go ahead and just use mean squared error loss. And then the optimizer, we'll use the atom optimizer. So we'll say torch optim atom, pass in our model parameters, and then set our learning rate to be 0.001. Let's go ahead and call our model. And you should be able to see now we have this LSTM of 100 neurons, basically then going into one single output. Okay, so now it's time to actually train the model. And this is essentially the same code as we did last time, except now we're going to train it for much longer. So we'll say epochs is equal to 100, and you can train it for more if you want, but after 100 epochs, you should start to see some good behavior. And then what we're going to do is I'll keep track of training time by saying import time, and say my start time is equal to time.time. And at the end of all this, what I'm going to do is basically grab my current time and subtract my start time from it. Well, actually, that's not necessary there. And we'll say total time is equal to that. And we'll print out total time divided by 60. So we get out how many minutes it lasted. So what goes in between is just the training. So we'll say for every epoch in range of epochs, and if you want, you can say for I in range epochs, doesn't really matter what that is. We'll extract the sequence and label from the training data. So say for sequence and ytrain, in the training data, go ahead and reset the parameters and hidden states. So we'll say optimizer, 0 gradient, and then we'll say model hidden is equal to that same tuple we did before. So we'll just scroll up and grab this guy. And there we reset the hidden and cell state. And then finally, let's grab our prediction. We'll say y prediction is equal to model sequence. And then we'll say loss is equal to criterion, comparing our prediction to the correct y train value. And then we'll say loss backward and optimizer step. Okay. And then finally, we can also print out the result for that particular epoch. So we'll say print, this is just the tracker, essentially epoch, pass in that particular epoch, and then the loss and we'll just pass in the loss item. Okay, let's go ahead and run this, make sure we didn't commit any typos. So it looks like, oops, had to delete self there. So this should actually be not self, but the model, because we're calling it off this model created up here. So apologize for that typo. But now let's run this, and that should work. So you should see the first epoch come out, perfect, epoch 0, epoch 1, and I'm going to fast forward in time until this is done training. Okay, that has finished training for me, and recall that our values are normalized, so don't be surprised if you're getting extremely small loss values. These are the loss values on the normalized data. So what we're going to do here is at the very end, you see it took about 3.5 minutes to run all this. What I want to do now is I want to go ahead and do some comparisons of our results on the test set. But then what we'll also need to do is invert the normalization to actually do kind of a plotting of the results and see how they compare. Let's run predictions and compare against that known test set value. So I'll say future is equal to 12. I'll set my predictions, so I basically add the last window training values to the list of predictions. So say my prediction is equal to train normalize minus my window size all the way to the end. And I'm going to have this cast as a just normal Python list. I'll set the model to evaluation mode, and then say for I in range future, what I'll do is set up my sequence. Scroll down a little bit. Set that up just as we did last time to a float tensor, where my predictions from minus window size all the way to the end. And then without updating any weights, we'll say with torch, no gradient updates, and then we'll copy and paste that model.hidden command just as we did before. So we scroll up here, essentially copy this, and then finally get our values. So we'll say predictions, append, model sequence item. And before we run this, let's make sure we say this is preds plural so that it matches here and here. Okay, so we go ahead and run that. That should pretty much be instant because we're not evaluating anything. We're just predicting into the future. And if we take a look at our predictions, starting from the window size forward, these are our truly predicted values. These are values that we try to predict that go into the test set. However, note that they're all normalized. If I were to take a look at my original Y values and take a look at the last couple ones, they're at a completely different scale. So what I need to do is invert the normalization on this, which also means I need to make sure that these predictions are in the right format. So how we can do this? Well, luckily, the scalar object has an inverse transform method that you can simply call. So I'll say go ahead and call inverse transform on the NumPy array of the predictions window size all the way to the end. And we have to actually reshape this for scikit-learn to accept it. I'll reshape it -1 by 1. Okay, so these will be our, what we'll call true predictions. So we run that, and we check out what our true predictions look like, and now we can see they're at the correct scale again. So let's go ahead and grab from our data frame, recall that we had this S4, etc. long column name. Let's grab the very last 12 values here. And these are the true correct values, and these are our predictions for those values. And you can already see they're kind of at the same scale, and they seem to have the same sort of behavior of like increasing and then probably maybe decreasing after this kind of a December month, so we can see the decrease there. Let's go ahead and plot these out and see how well we actually performed. One thing to note though is that the original values in this data frame, they have a date stamp connected to them. However, our predictions don't. They're just in kind of this weird NumPy array. So what we need to do is add in those date timestamps so we can actually plot them out. Technically our work has been done. This is technically just for plotting out. So what I will do here is I will say x is equal to np arrange starting from 2018 0201, comma, go to 2019 0201. And the reason I go 1 month further into the future is because I'm technically going up to but not including this date. So I start at the correct date here in my test set, but I'm going 1 timestamp further. And then what I want here is we'll say that my data type is date time, 64-bit, and then in a set of braces, I'll say capital M because it's monthly. And then we'll go ahead and run this as type. And then say, well, let's go ahead and just run this so we can see what X looks like. So this is what X looks like. And what we need to do is make sure that the index here for our data frame has the same data type. So if I say df index, notice that it also has a datetime object. So let's go ahead and plot this out. I'm going to just copy and paste the plot code from our notebook that's in the lecture, because it's actually code that we've just seen before. Essentially the same code we used last time, except now it has a nicer title. We added a grid, set our figure size. Main things we're doing here are these two lines. We're plotting out our original data frame, and then also plotting out these X timestamps against our true predictions. Go ahead and run that and show it, and we can see here the orange prediction against our test set. So let's go ahead and zoom in and just plot out at the very end of this plot. And again, I'll be copying and pasting this code from the lecture notebook, and this essentially zooms in on that particular portion. We set up the figure, the title, the Y label, the grid. We also have a little bit of auto scaling, auto formatting, but the main two lines here are the same plots as before, except now we're just slicing starting at 2017. So when we go ahead and run this, we can see the results. And your results may be slightly different due to the way LSTM networks work, even if you set the same manual seed that I did. But overall, you should hopefully see that after 100 epochs, your network began to learn the behavior. So it should go up and down kind of at the same rate that the original data does. And we can see that it's beginning to learn that behavior. So lastly, what we're going to do is we are going to forecast into the unknown future. So far, we've only forecasted into what we did know of that test set. So what we're going to do is we're going to set our model back into training mode, except now we'll go ahead and train on essentially what is all the data. So what I'm going to do is I'm actually just going to copy and paste this code from the notebook, because at this point, we've already seen this code twice already, once in the basic RNN and then a second time in this same notebook. So I'm just going to copy and paste, and none of this code is really new besides the formatting because it comes from the lecture notebook. But basically, we're setting 100 epochs, we're setting our model back into training mode, but what I'm doing now is I'm using the entire data set. So the main three lines are these three lines, and essentially fit transforming on all the data. So we want to make sure we refit our scaler, because we're now introducing different X mins and different X maxes, not just on the training data, but now we get to use all the data that was in Y. We go ahead and convert that normalized data into a tensor object with PyTorch, view it correctly, and then we have pass in all that data. So all that Y normalized data along for our window size into that input data, and now I have all data. And then all this code is what we've seen before. We have our start time, epoch, training, printing out results. So let's go ahead and train 100 epochs on this model. And now we're using all this data. So I'm going to hop forward in time until this is done training. All right, so I finished training for 100 epochs. Looks like we're getting a pretty small loss values, so that's good. Let's go ahead now and predict future values and then plot the result. Recall that right now what we're going to do is we are actually going to forecast into the unknown future, which means, theoretically speaking, there's no real way I can assess these forecasted results because there's no correct value to actually compare them to. It's all into the future. So let's go ahead and just code this out to forecast into the future. I'll say my window size is 12. I'm going to forecast a full year into the future. So I'll also say my future is 12. And then L is equal to length of Y. And just as before, we've essentially already seen all this code. I'm going to grab my normalized Y values and then go from minus window size all the way to the end to essentially set up my forecasting set that I'm going to forecast off of. And then we'll convert that into a list. Because remember, we need a minimum of 12 values to predict value number 13, which is why I'm grabbing just from the very end, and then I'll supplement one by one my actual predictions. Then we'll go ahead and say model eval, and for I in range future, essentially for 12 points ahead, what I'm going to do is say my sequence is equal to torch.float tensor. Grab those predictions and then go from minus window size all the way to the end, essentially increasing one by one. And then without updating any of the weights, we'll say with torch no gradient, what I'll do is say model.hidden is equal to, and here I'm just going to copy and paste the same commands we've been using to set up the hidden state and the cell state, which is right here. So go ahead and copy that. We're essentially doing the exact same thing as before. None of this is really new. We'll take those predictions and then append, saying grab model sequence, and then grab the item off of this, since this is just a single number. And so we just keep repeating that result, essentially moving up one step at a time, and this minus window size automatically is going to grab more and more of our forecasts or predictions, and then eventually we're doing kind of forecasts off of forecasts. So finally, what we want to do is, since we want to plot this out, let's go ahead and inverse that normalization. So outside of this for loop, in fact, let's go ahead and just run this for loop. Outside of this, we'll say our true predictions is equal to grabbing our scalar object and calling inverse transformation on the array of our predictions. And we need to reshape this to be -1 by 1 in order to fit correctly with this scikit-learn function. So now we have our true predictions. Let's go ahead and take a look. So here are our true predictions, and the reason I say true predictions here, true doesn't mean that these are 100% correct. True just means that they're actually now in the correct units. They're no longer normalized. If we were to take a look at the actual predictions the network spit out, those were normalized values. So just keep that in mind. Okay, so we have these predictions scaled correctly. Now let's go ahead and just plot them out. And what I'm going to do is I'm just going to copy and paste our plotting code from the notebook, since it's essentially the same code that we've seen before. And we'll go ahead and set the date range for the predicted data. So I set this date range, and then I go ahead and plot out, add a couple labels here, go ahead and run that, and now we can see our forecasted result. And just with our kind of plain eyeballs here, we can see that this is a pretty reasonable forecast. It's continuing that upward trend, as well as continuing the sort of seasonality behavior in these spikes. And we can go ahead and zoom in on this to get a better look at that. So I will zoom in, essentially editing the range on the x-axis that I want to view, saying, okay, only view from 2017 onward. And we can see here, zooming in, it looks like the behavior makes sense. Keep in mind, the actual plot won't connect from the real values up to the forecast values because there's technically two different plots. So here's the plot of the real data, and then here are the plot of our predictions. So keep in mind that line, the reason there's a gap there is not because we're missing any information, but just because of the way these plots work. Since they're kind of two separate plots on top of each other, there's technically no connection there between the blue data set and the orange data set, which is good because we kind of don't want to imply that they're from the same data set. The orange is forecasting into the unknown future. All right, so that's it for this series of lectures. I hope you can now see how you can use our functions in order to forecast on your own data sets. I want to quickly point out that our lecture notebook, if you kind of scroll through it and then scroll all the way to the bottom, we have some convenience functions for you that essentially automate a lot of this work. So to save time in the future, we've written a function that will take in a time series training dataset and output a tensor of sequence labels. So you can check out this sort of cell functionality, essentially create train data. And we made this specifically for you to kind of easily work with your own datasets. All right. Thanks, and I'll see you at the next lecture.